Okay, so now it's my great pleasure to introduce Alexandra Likic to you. So she will be the moderator of the next session, which is about the focus talks, so in which we have a couple of small talks, short talks about different research projects going on in Delft and around. So Alexandra is an assistant professor here in Delft in the AV faculty, EMCS. She holds a degree, bachelor, a master and a PhD degree from University of
Belgrade.
Belgrade, right, in electrical engineering. And you're also an expert on electric grid optimization and control and stability. So I'm very happy that you're here and moderate this session.
Thank you very much, Matthias. We have our first speaker, Matthijs de Wert, with the title, The Center for Energy System Intelligence, Interdisciplinary Research on AI and Energy. And shortly, Matthijs de Wert is a full professor on algorithms for planning and scheduling and section head of the algorithms group at the Delft University of Technology. An important challenge for him is to identify how AI can contribute to the energy transition and sustainability of our society and what is needed to speed up such developments. Together with Yashar from Rotterdam School of Management, Erasmus University Rotterdam, he chairs the Center for Energy System Intelligence in context of convergence. So I will call Matthijs to join us. And let's try to find the presentation. The first one is this one.
No.
So it doesn't open.
That one.
That one. Alex, you'll have to. Okay.
Good morning, everyone. Yes, I'd like to pitch to you what we do in this Center for Energy System Intelligence. So I'm not going to talk about my own research on algorithms for planning and scheduling in this context, but it's more like a pitch about how we organize actually part of the institute. It's sort of a mini institute that is made possible by the convergence of the universities Delft and Rotterdam. So I do this together with Yashar Ghiassi from Erasmus University Rotterdam. And the aim is to build up a research ecosystem that goes across the universities, specifically on the topic of AI and energy. And the goal of these collaborations eventually is to really have good research projects. As we've already seen in the plenary talk this morning, there are great challenges related to the energy transition and opportunities for AI to contribute to that. The challenges are related to the operation of the system, the operation of energy services, of the uses of the system, investment decisions, and also doing the maintenance of such a complex infrastructure can be improved by using the relatively novel technologies coming from the AI domain, like machine learning, planning algorithms, autonomous agent systems, computer vision, and the interaction of human and AI. And not only for these type of projects, we will need expertise from AI and from energy systems, but also on energy markets, regulation, social behavior. And of course, to bring these projects to make impact with these projects in practice, we need to collaborate closely with the industry, with energy companies, and with system operators, and with governmental organizations. So these parties we aim to bring together in this center and jointly talk about mutual interests and get to projects where we bring together the right data, the right tools, and eventually the right solutions. So how do we do that? Well, we start by bringing together the professors from these institutes on specific teams. try to find matches where they can complement each other and learn to speak each other's language. And then identify themes, topics for which we see there's a current need, there are good opportunities for funding, there are partners outside the universities that are interested in these challenges. And for those, we then aim to write good proposals in the end and get the research going. So we also, through the Institute, make connections to other parties, and we aim to help researchers to share data and to easily find data relevant for this type of research. And as you may know, for AI, it's important that you have good data to be able to learn the right patterns to train your methods. So just a sample, so how do we do matchmaking? Well, we organize a few sessions, mainly for the assistant and associate and full professors. So in those sessions, we talk about longer-term goals that we have within our own expertise, within our own research area, but also trying to make that connection to the expertise of others. So I'm giving this pitch for these professors, the ones that have not joined yet, please join. I'm also giving this pitch for everyone else because in parallel to the matchmaking, we are organizing ourselves along a number of themes. And hopefully, this can help you to find the right people. So you can approach me or any of the theme leaders if you're interested in one of these topics and with the background knowledge that we really aim to approach this with an interdisciplinary team. So I'd like to highlight two of these. Two of these that are not maybe that close to most of you, because I think you can imagine what we can do within congestion, but maybe not about, maybe you don't know that much about green AI and AI for energy meteorology. So the Green AI initiative is the work by four of my colleagues, Aaron Ding, Luis Miranda da Cruz, Charlotte Frenkel, and Raj Bishnoi. And they sat together and said, okay, if we're going to use a lot more AI, then that the AI itself is also going to use a lot of energy. What can we do about that? Well, partly, energy is, of course, the use of energy starts from the devices, the computation, the sensing, the acting, and the communication. But also, it matters very much how you then use those devices. So throughout the whole development cycle, you need to take into account where the energy is used. And the design decisions should be taken given the understanding of how much energy is used. And for that, we need tooling. And with that, we can then have energy-aware AI systems in application areas, of course, in the energy system itself, but also in health, mobility, and observation, for example, of plant crops. So they discuss together and have a much more detailed plan on this. And currently they are in a phase of inviting industry stakeholders to identify now with them what are the most urgent things that we can do with the expertise on both hardware, software, and the tools. The other example that I'd like to highlight is on energy meteorology. So this can be seen as a relatively new field where we use insights into atmospheric sciences to inform decisions in the energy system. In particular, in the context of this transition, and that we are going to use more and more renewable energy. For example, by better understanding the atmospheric circumstances, we can much more accurately predict the production of a wind farm. So at the bottom here, every gray line is the production of one turbine in a wind farm. And there's, we can of course work with the average, it's the blue line there, but the detailed understanding and also the detailed control of the wind farm can improve the output, and the detailed, a much more accurate prediction can help in adjusting our use of this power. Also, the more and more of these wind farms we install actually affects the climate, it affects the weather. What we see here at the bottom is a graph that represents the loss of a wind farm caused by other wind farms in the neighborhood. If they had not been there, this wind farm would had produced a bit more. So this the scale here, I'm not sure if everyone can see that, it's between it's up to about 10%. So this effect can influence our future investment decisions in where to build new wind farms and whether to build them at all to the states. So here the current state is writing a survey of these challenges and also how AI can play a role in making these better predictions and models of the atmosphere. And we're working towards a first resource proposal. Oh yeah, one final note. With a group of students, we're also working on an open source home energy management system. So if you're interested in that, please let me know. Then, next steps for you, for us. We will continue on these themes. We hope to discover more themes that can have an impact in practice and have the interest of the researchers in Delft and Rotterdam. So for you, please join. Tell me what you would like to do. And if you are outside the university, please contact the people here on the screen for those respective topics, or me if you have any other question and you'd like to find out what expertise there is in these two great institutes. Thank you for your attention.
Thank you very much, Matthijs. We'll have a short question and answer session at the end of all presentations together. So I will announce the next speaker now. I'm not very proficient with Alex. You have to help me with this computer. Okay. So I will invite now Pedro Vergara Barrios with the presentation on generative AI for distribution system planning. Pedro is an assistant professor at the IPG group at the Delft University of Technology in the Netherlands. From 2019 to 2020, he was a postdoctoral researcher with the Eindhoven University of Technology, also in Netherlands. He holds a PhD degree from the University of Campinas in Brazil and from the University of Southern Denmark in Denmark. So, Pedro, I will just now find your presentation, which is this one. And let's hope enable editing. Okay. Okay. Did it show? Yes. Okay, perfect.
Thank you. Thank you. Good morning. Yes, today I will talk a little bit about the work that we are doing within one of our research projects here at TU Delft related to the use of generative AI for distribution systems planning. So I will start talking a little bit first about the context of the problem, and then we'll go right and dive into how can we use generative AI for distribution system planning, and I will present very shortly one case study. So, yeah, I believe that we are all aware that in the context of the energy transition, a large number of these different energy resources have been added in large quantities to the distribution system infrastructure. So we're talking about electric vehicles, electric heat pumps, residential batteries, solar panels. Large number of these resources are creating what we are all aware here in the Netherlands, that is congestion. Congestion creates lack of capacity, right? So the current infrastructure is operating to the maximum capacity, and I believe you are aware of this figure in which the system operators in the Netherlands used to represent sort of the state of the capacity of the infrastructure in the country. So we see here is that the red area is generally no capacity left for new connections, right? And the yellow and orange is some capacity left under some operational constraints. So this is a pressing issue in the country, but how exactly congestion looks like? Well, if you see here this figure, It comes from real measurements from one project that we did together with the system operator, Alliander, and it relates to this area about Slaughterham in Amsterdam. So what you see here is measurements from medium voltage cables that supply the energy to this area. And what you see is that congestion is called when the capacity of this cable surpass certain threshold that is defined by the operator. Right? So what we see is that the distribution system infrastructure is operating then to the maximum physical capacity. But no capacity is available in this case during these short periods of the year. So what you see here is that we are actually surpassing this predefined threshold only a couple of periods during the year, right? So the question is, we need to quantify. We need to know how often this congestion happens, this phenomenon congestion happens, so we can prepare ourselves, prepare the infrastructure, so we can make better use of the current infrastructure. If we assume that we don't know how often we are operating closer to this threshold, then we will assume that there is no capacity left throughout the whole year. So these measurements that you see over here are usually are the case of most of the medium voltage network in the Netherlands, residential, with a large part of electric heat pumps. And this is the case more during winter, right? In which the most of the demand goes to supplying the heating of the residential users. So how can we use generative AI to sort of help us to solve this problem? And we are aiming from the perspective of planning, right? So if you are aware, or if you are not aware, generative AI is this term that we use to sort of represent the models that have the ability to produce new content, new and unique content. And this includes text, images, audio, and video. You see some examples here from using one generative AI, the DALL-E model, very, very famous, in which you can actually request to the model, give me sort of figures of pictures of people, or in the case of the figure at the bottom, some castles, and you generate. These are not real people, not real castles. So because of these properties, then generative AI is a valuable tool already in many industries, such gaming, entertaining, and product design. The question is, how can we make use of generative AI in distribution system planning? What we are doing is taking advantage of an excellent feature of generative AI algorithms that is called condition. So basically, we can sample from these algorithms with one particular condition that we propose to this model. In the case here, we say to the model, give me a picture of a castle, right? That's the condition that we are putting into the model. So how can we make use of this conditioning for electricity infrastructure planning? Well, what we are doing is making use of generative AI to generating time series energy data generation, right? We want to characterize how people are using energy in order so we can use it to better plan the infrastructure. There's a large number of models available, right? They have multiple features, and some are simpler than others. But when we go to the state of the art, so these are different models available. Let's not go into details. But what you can see here is that many of these models sort of fail to represent the most important features when it comes to energy data generation, which are the peak, right? The peaks are the most important. So what we are proposing is models that are capable, so we see here the original data, and the models that we are proposing are capable of replicating, so creating unique profiles, learn following the statistical behavior of the original data, capable of learning these particular features that are important for energy system planning, which is the peaks. So you see over here, the comparison of the models that we have developed here in the bottom that we call energy diff and real data, and some more classical statistical models. So you might see, well, it's quite difficult to see here the comparison of these models, but when we go to a lower number of dimensions, you just see over here that classical models, they sort of only are capable of mapping one part of the statistical space, right? While the models that we develop sort of cover more these features. How can we make use of this data that is being generated? So let's see the case of solar penetrations, right? So what we aim to do is to develop frameworks that allow grid operators to make risk-informed decisions before committing to network reinforcement. So basically is models that allow the operators to know if reinforcement in the network, in the infrastructure is needed. So let's do the case for the solar PV hosting capacity. So what we do over here is that we are analyzing how the sort of infrastructure is growing in the decades sort of time ahead, but we are making use of data in the 15 minutes resolution feature. So how do we do it? We make use of the condition features, and we generate large number of profiles, right, of energy consumption to create this kind of figures that you see over here. So the 0 point that you see over here, this is today, right? And what you see in the horizontal axis is annual energy consumption growth in terms of percentage, right? How is the energy consumption gonna grow for the next 1 year, 2 years, 5 years? We can impose that to the model, and then the model will provide to us 15 minutes resolution data for 1 year for a large number of consumers. So it's sort of forecasting or predicting the energy in the future. And then we have in the vertical axis, we have the PV capacity that, again, can follow any trend, 10, 20, 30%, 40% compared to the case now. And we can follow, for example, the current trend when it comes to the penetration of these resources. So what the generative AI algorithms allow us to do is to sort of generate the data, so we can try to fill in this figure in which the green area, sort of the safe under certain operational condition, and for the case of this PV, it relates to voltage issues. So what you see over here, and just one example, is that, okay, for this particular case study, we generate the data, we sort of analyze the performance of the network, and what we see over here in this point, that is called 40%, is if we have 40% of annual energy growth, right? You see that we are sort of operating in the border there with the caution area. But if we allow 5% of the risk, then we can see that we have 15 more capacity with only 5%. Right? So this is what generative AI can provide us, data in order to make detailed analysis of the risk involved in operating the infrastructure. Of course, if we allow higher risk, then we sort of increase the safety area, right? Which is the green that you see over here that is growing. Operators, they dislike risk, right? They will never operate under certain risks, but still we can use generative AI to sort of assess these risks. If we assume, for example, that we are operating in point A, in which we assume that we are operating with a 5% risk, then we can make use of the generative AI algorithms to analyze what is the probability of these events happening. So what you see in the blue point is the real measurement data. So this is the data that was used to train the generative AI algorithms to sort of fill the full figure. So what you see is that although we are allowing the infrastructure to operate with 5% of risk, this has never happened in real time. Right? So this allows us to quantify the risk. Some conclusions. Generative AI, we are using it to help to overcome sort of the lack of data, right? Because we need to quantify congestion, but in terms of how often it happens, right? And generative AI help us to sort of populate algorithms with data so we can make a more risk-informed decisions on the infrastructure. And of course, planning, considering accurate, this case generation and consumption data modeling allow us to reduce uncertainty when allowing certain risk. All the research from the PhD, Weijin and Mauricio, together with TU Eindhoven. Thank you very much.
Thank you very much, Pedro. So I will call Eliška Greplova. Doesn't work. Okay. I'm sorry, technical problems. Okay, good. So the title of the presentation is Exploring Biological Neuronal Correlations with Quantum Generative Models. About Eliška, she's an assistant professor at Kavli Institute of Nanoscience and the group leader at QTech at Delft University of Technology in the Netherlands. She leads the Quantum Matter and AI group, where she works at the intersection of quantum technologies, artificial intelligence, and condensed matter physics. Previously, Eliška was affiliated with Microsoft Research, ETH Zurich, Aarhus University, and the Max Planck Institute of Quantum Optics. So, if I am proficient enough, I will manage not to find the presentation. The presentation is not open. It's not open. I'm sorry for the delays.
Thank you. Hi everyone. Thank you for the kind introduction. Thanks for having me here. Sorry for the technical difficulties, but we made it work. So I will give a short pitch that has a interdisciplinary components in AI, quantum, and a little bit of a neuroscience. It has a little bit tangential connection to the energy transition, but hopefully I will manage to persuade you during the talk that it does. So one question that came up, so I am based at the Kavli Institute here in Delft, and that has a both bio, specifically nanobiology institute, and also quantum research where I am working. And so I've been watching my colleagues on a bio side studying all of these aspects about how biological neural networks, like the actual neurons in a biological tissue, exchange information. And this is one of the super important questions of our time, right? Because just understanding how our brains process information, that's super key, just, out of fundamental science. But then we also know that our brains are pretty great at processing this information. You hear a lot of, famous AI scientists say this sentence that, oh, surely human brain doesn't do a backpropagation because that would be super inefficient. Just training a neural network, and I will come back to this later in the presentation, that distinguishes cats from dogs, that are pictures on the internet, actually takes a lot of electricity and a lot of GPUs. And human brains are pretty sophisticated, so they must be doing something different. And so this is this interesting part where sort of computational science and a neuroscience meet at the boundary of these questions. And so what people usually do is something like this, that you can make a biological tissue. I will not go into the questions of how this works in the lab, but roughly speaking, you can just grow some neurons in a petri dish, place an electrode under them and watch them spike. And what you will get is something like this. We call it a spike trains, and they are just series of when which neuron. For example, this would be one neuron, this would be other neuron, and you can sort of measure when which spiked as a function of time. And then you can think about what are the emerging collective properties of how these neurons are spiking and how this is related to what kind of stimulus I gave to my neuronal network. And so if you can do this experimentally, you can of course also do it with some computational model. You train, for example, a big machine learning model that is going to reproduce this neural network and give you the spike trains. And then the question comes up if it's possible to interpret this model and actually learn something about the underlying biology. So already the previous talk nicely set me up for this, so I don't have to tell you much about machine learning because you hear this all day long. But you know already that the neural networks are basically almost universal functional approximators that have these layers of neurons that are connected by weights that we train. And then we can do, and this was the first, application of neural networks to distinguish two classes of images. For example, I can tell Albert Einstein from a girl with a pearl earring. And then you can also do this other thing that we heard about in the previous talk already. You can reverse this process. And when I use my network to learn distribution of how typical Einstein looks like and how typical girl with a pearl earring looks like, I can make that network learn those features and then respond to the prompt to create a new combined objects that combines the properties of those distributions. What we do in quantum machine learning is very similar, but instead of these classical neurons connected to the weight, we basically take a quantum computer. This is one of the model of quantum computing where each of these is a quantum bit. This is the time axis, and this is me applying quantum operations. And then I can parameterize those quantum operations. Those are these thetas here. If this is new, don't worry about it. Basically, I am just saying that I can train parameters of my quantum computer the same I would train a weights in a classical neural network. How I do it technically, what exact algorithms I am using is slightly different, but this quantum circuit is not that different from this Einstein with the pearl earring that I showed you in a previous slide. And so, thinking about all of this, what we were interested in was this. Can we make a generative model that is going to reproduce the distribution of the biological models that our colleagues in the Kavli Institute are measuring in the lab? And more interestingly, can we make it quantum? Why were we interested in making it quantum? These classical generative models, as you probably hear about in the news and generally when people discussing them, is that their interpretability can be really tricky. And then they start spitting some things and you maybe don't know why, because the amount of parameters that they have is really enormous. And in quantum machine learning community, because of the expressivity of these small quantum systems, there is a first sign that actually you can use much smaller quantum model to produce classical data. So we built such a quantum generative model. I will not go into the detail. We call it a spike gun, and you can read about that in our paper. And we actually found out that we can reproduce the behavior of these biological neurons from one of these standard biological data sets, both spatially and time-wise, with a number of parameters which was scaling linearly, compared to the classical models where you would have much more unfavorable scaling with the size of your input. So for us, this was a very prominent first sign that we can actually compress the size of the network that we are training, and when we have less parameters, we can plot their correlations and explain a little bit more what the network is doing. This is the example of these correlations. I will not go into the detail. It's just a way to say that, from the correlations that biologists care about, what this quantum model is producing is the same that they measure in the lab, or same or very similar. So quantum machine learning has still super many open questions. we don't even have one killer example like a Shor's algorithm or something like that, where there is one thing that we say, oh, this is a clear computational quantum advantage. At the same time, we have a lot of computational models and first generation of quantum computers to experiment with. And when we experiment on these real world examples, we actually get some first very promising signs of success. And today I was trying to give you an example of such success with the quantum machine learning for activity of biological neurons. That's it from me. Thank you for listening. If you have questions, talk to you in the end.
Thank you very much, Eliška. I'll have a support also. So I will invite Francisco Horta Ferreira da Silva with the talk on quantum correlations for energy systems. So Francisco is member of a pre-spin-out team at TU Delft, developing real-world use cases and applications of entanglement-based quantum networks. Previously, he completed his PhD at TU Delft under the supervision of Stephanie Wenner, having done work on quantum repeaters. Before that, he received bachelor's and master's degrees in engineering physics from the University of Lisbon.
Thank you very much. And good morning, everyone. Does this work? Yes, perfect. So indeed, my talk is about quantum correlations for energy systems. And I'll start by explaining what it is that I mean by quantum correlations. So I think up until now today, whenever the word quantum popped up, it was associated with quantum computing. I'm going to talk about something slightly different. Quantum correlations are the correlations that arise if one measures entanglement. Entanglement is at the heart of quantum communication, and one can think of networks or a quantum internet as infrastructure that allows us to distribute and establish entanglement between remote parties, and these parties can then consume this entanglement to execute a variety of applications, such as directly measuring them to obtain quantum correlations, with the benefit that these correlations you can generate with entanglement correlations that are classically impossible. So just a couple quick messages on entanglement. One, to create this between distant parties, one needs some form of a physical connection between the two of them. This could be optical fiber, could be free space, it could be a satellite. You need some way to get light across, and this process takes time. If nothing else, the time light takes to propagate between the two distant parties. Then if you want to use it, if you just want to consume it to generate these quantum correlations, that happens as fast as your device is at performing a measurement operation. You obtain the correlations right away without further need for communication. And one attractive aspect of looking at potential applications of these correlations is that they don't place very stringent requirements on the quantum devices you need. You need to be able to make entanglement very fast, and you need to be able to measure it. But you don't need long-lived quantum memories, and you don't need many qubits, and you don't need to execute complex circuits on them. So before going to a somewhat practical example of how these correlations could be used, let me introduce the concept of non-local games. So in a non-local game, we have multiple parties, in this case 2, that receive inputs and must produce outputs. And they are said to win the game if a win condition is verified, and this win condition is some relational expression between the outputs and the inputs. And crucially, we do not allow the parties to communicate after they've been given their inputs. They may communicate ahead of time to agree on a strategy, but once they receive their inputs, they need to produce their output without knowing the input of the other party, which is where the challenge comes from. And what makes this interesting and how this relates back to the purpose of the talk is that for some appropriately designed win conditions and taking advantage of the fact that entanglement gives rise to classically impossible correlations, there are win conditions for which the two parties can win more often if they have access to entanglement. And basically the idea is that The parties have entanglement, they receive their inputs, they measure their entanglement in a basis that depends on their input, and then they make a decision based on the output they get from measuring the entanglement. And so a concrete example of this is the CHSH game, which is the first and best well-known example of this concept. Here the inputs are binary, you get either a 0 or 1. The decision is also binary. The players must output either a 0 or a 1. And the win condition is the AND of the inputs should be equal to the XOR of the outputs. So if both inputs are 1, you want the outputs to be different. And for any other case, you want the outputs to be the same. It's not super trivial to see that this is the case, but if you sit down and you write it out, you can quickly conclude that classically, meaning if the players do not have entanglement, they can do no better than winning 75% of the time. If they have entanglement and with correct strategy on how to use this entanglement, they can bump this up to 85%. So we say that for this particular game, there is a quantum advantage. So this is still quite abstract and academic. Let's start trying to bring it closer to something that might be of practical interest. And for that, I will introduce this concept of latency tacit coordination problems. So first, let's forget about the latency and just look at a tacit coordination problem. This is a problem in which we have multiple parties, so at least 2, which each make an observation, and based on this observation, need to make a decision. And this decision will be made in such a way to optimize an utility that depends on the observations and the decisions of all the parties. A latency tacit coordination problem is the same thing, but we assume that the parties do not have enough time to communicate in between making the observation and taking the decision. Presumably because the problem in which they're interested in is very latency sensitive. You don't want to spend the time in communicating, and perhaps you can see the connection between this and the non-local games that I've been talking about. And now let me give a more concrete example of such a problem. And for that, I'm going to look at something called load balancing. And so the scenario we have here is we have 2 computing servers, which are classical servers. In this case, they execute classical programs. And we have processing jobs, computing jobs that arise randomly and with a processing time that is also randomly distributed. And the goal of the players here is to route these jobs to the servers in such a way that load is balanced and that we get to minimize the average waiting time until a job is processed. So the players are these load balancers, the observations are the processing times of the jobs, and the decisions are to which server to route the job. And given some assumptions on the specific characteristics of the servers and the distribution of the processing times of the jobs, which I will not go into right now, we actually find that basically this maps to a non-local game that has a quantum advantage, and under these assumptions we find that we have a lower waiting time if the players are allowed to share entanglement than if they are not. And so this is one example of how one can take this concept of non-local games and show a quantum advantage in something approximating a real-world problem. Now, this has still nothing to do with energy systems, so maybe I can start heading in that direction. And unfortunately, I don't know exactly how this applies to energy systems. I can make some hypotheses, and it doesn't seem completely unreasonable that it would apply. But basically, what one would need to do is to design such a latency tacit coordination problem that exhibits a quantum advantage in such a way that more or less closely models something arising in energy systems. So I know very little about energy systems, but I made an attempt here at imagining what this could look like. So perhaps our players are agents that are connected to a power grid. Maybe they both consume and produce energy. Sometimes they have too much energy, more than they need, so they want to send it back into the grid. Sometimes they have too little, so they need to consume. So perhaps they want to decide when to send, when to get back, how much to send, how much to get back. And perhaps their utility is some function related to grid stability. I don't quite know. I'm not sure how reasonable of an example this is. But basically, one can think about this as there being a design process for coming up with use cases in which we'd have a quantum advantage of the type I showed for the load balancing example. So first, one needs to think of, so who are the players? Who are the agents that make the observations and the decisions? What is it that they're observing? What is the characteristic of their environments that they look at and base their decision on? And what is the decision they're taking? And finally, where the biggest challenge comes in, what is the utility that they're trying to optimize for? And how can we relate it back to a known no-local game that has a quantum advantage? So to conclude, these latency tacit coordination problems are a potential near-term application of quantum communication in particular. And I think they're quite attractive in this sense because indeed they don't place very stringent requirements on what your quantum system needs to do. There are some known fairly academical toy model examples of such problems that exhibit quantum advantage. And it does not seem super unlikely that maybe one could come up with similar problems in the field of energy systems. And so if this talk sparked some ideas and you have thoughts on what such problems could look like, I'd be very happy to talk to you and hear your thoughts. Thank you for your attention.
Thank you very much. So now we have Matthias Müller with opportunities and challenges of quantum computing for CFD applications. Matthias is an associate professor of numerical analysis at Delft University of Technology. He holds a PhD degree in mathematics and joined TU Delft in 2013. Matthias' research focuses on the development of numerical methods for solving differential equations, both with classical and quantum computers. So.
Okay, thanks very much, Alexandra, and thanks for fixing the technical issues. Yeah, so this also doesn't have to do directly with energy grids. Maybe if you think about designing turbine blades of wind farms, then you could use the term CFD there. And let me start from the beginning. We are not looking at the NISQ era. We are really looking at the FTQC, that means fault-tolerant quantum computers. That means those which are really able to run huge computations with many qubits, some kind of 100 qubits, logical qubits, I should say, and very deep circuits. So what this is a joint project together with Fujitsu Limited in Tokyo, Japan. And so you see our team right now and the Fujitsu team in Japan, most of them, some are in UK. And the idea that we have is to write a quantum start-to-end application for fluid flow. So you might ask, why? I mean, there is CFD, commercial CFD applications, academic ones, all over the place. Yeah, so these are just a few examples. You have it in aerodynamics, you have it in aeronautics, you have it in climate and weather modeling, in biomedical modeling, everywhere. So it seems like CFD is kind of fully established. Why quantum? Well, CFD is not equal to CFD, and let's say the real challenge of CFD is turbulence. Yeah, and I've put up some very old drawing from Leonardo da Vinci, who already drew turbulence when water flows into something. And the kind of the real analog in real world, yeah, there's also water flowing into a basin. And you see the three stages: laminar, transitional, and turbulent. Laminar is easy. You don't need a quantum computer for that. Also transient or transitional is not the real challenge. It is turbulence. And what is challenging about turbulence? Well, it's the scales. And so when you look into water, air, or something that flows, you typically have these very large scales. They are simple to resolve. Resolve means really have a computational grid that is as large or as small that you really capture this entire, this doesn't work, so this entire swirl. Yeah, and if you then go down the, let's say, the energy scale, then we get smaller and smaller and smaller scales. And all of them, and when we are talking about turbulence, it is the small scales that do matter. All of them have an impact. So what you can do and what is typically done today is you're modeling them. Yeah, and there you have a kind of, you can play between how accurate can you be for how large is your system you want to simulate. Yeah, so what today state of the art is, if you really want a full system for me would be a complete aircraft or maybe a wind farm. Yeah, then you can't do very detailed turbulence modeling. Then you do something like Reynolds averaged Navier-Stokes or unsteady rents. Yeah, very inaccurate, but you can do full system. Somewhere in between is the LES, large eddy simulation. That means you resolve as much as you can, so the large eddies, but this last bit, so the last very tiny ones, you can't resolve. Yeah, and already there we can't do, maybe with the biggest supercomputers we can start to do, we can't really do full system simulation. Yeah, again, full wind farm. And yet a level more accurate would be direct numerical simulation. That means you're not modeling anything, you're simulating everything. That means you have a very, very, very fine grid. Yeah, that you can do at a component level. This is something that NASA did with a front wheel of an airplane, but it's unthinkable to do that at full system level, and not today, and not just today. Yeah, so it's really conceptually unthinkable. You would need factor 100 more than today's biggest supercomputers can do, both in terms of compute time and memory. And there are reasons to believe, and I hope I can convince you in the coming few minutes, that with quantum computing, one can do turbulent simulations at full, say DNS simulations at full system level. Yeah, and that's why we do it. So the vision that we have together with Fujitsu is to really implement something that is working, in the sense of, if today there would be a full FTQC, we really want to use it from start to end. No cheating somewhere in between. And that's why we started to really code down a quantum CFD code. So the mathematical tools is we use a Lattice-Boltzmann method underneath. And what we have there is kind of tool chain that really takes in a configuration, a grid, geometry, obstacles, etc. And then it is creating all the circuits. It is creating all the circuits for a concrete hardware, yeah, and then at the moment we are running on GPUs and CPUs in simulation mode, but we do everything, let's say, as honest as possible as you can do on a quantum computer, and then, yeah, you get out some nice pictures. So here I have nicer ones. Yeah, for example, this is a 2D flow around a, well, artistic obstacle, and on the right you see even a 3D flow. And what we can also do is resource estimation, like how much time, how many gates would this cost on a real quantum computer if it would be there. So if you have questions about this, we also have a poster, and you can always reach me. Thanks.
Thank you very much, Matthias. Now we have Sebastian Feld with Quantum Enhanced AI, innovating sustainable materials and structures in aerospace. Sebastian is an assistant professor at Delft University of Technology, Netherlands. He investigates how quantum technology might help creating near-term quantum applications, but also how machine learning techniques may assist with developing scalable quantum devices. So,
thank you so much. Hi, everyone. So today I would like to talk about a lab that we have that is called QAIMS. Thank you. And so the punchline would be quantum enhanced AI, innovating sustainable materials and structures, in particular for aerospace, but also in general. The story would go like this. So perhaps one of you guys already flew in an airplane and wondered, okay, we are almost in outer space and we are only protected by this thin layer of material against this pressure out there, or the missing pressure, what is fantastic. And it is also the case that this material protects satellites in real outer space against radiation, or if the satellites come back down to Earth, against the heat. And it's all this material that protects the people inside of this of these things. And what we would like to do is to use hardware and basically also software to solve those problems arising there. So a new computing paradigm called quantum computing, and some algorithms borrowed from machine learning. And this is then inside of our lab that we started, I believe, 2 years ago, QAIMS we call it. We are a couple of supervisors and a couple of PhD candidates, brilliant people. I would like to highlight Arne because he did these slides. I would never be able to create such like animation slides, etc. So props to him. And we teamed up those students. So Swapan and Arne are working basically on a kind of combinatorial optimization problem to create such material. And Philip and Kuhn are working on simulating what would happen, let's say, under some extreme conditions. Let's have a look into this. So optimization of laminated composite materials. What is a composite material? Basically something like fiber-enforced material. If you have a material in which some fibers are, this is a composite material, a comic example. And if you have lots of them, then you create a laminate. And these laminates should have some special properties regarding some stiffness. So depending on the forces you put on this material, they should or should not deform. In a nutshell, be very light but strong in a case. And to create this material, you can envision this as a puzzle or as an optimization problem. So you can have a look at the ply angles sequence, so how to stack these onto each other. Also, the thickness of the material defines how many layers you have. And then also the intrinsic properties of this material, but we leave this out. We just say, okay, this kind of material we have. And then you can represent this in a mathematical way to only have 12 so-called lamination parameters. So basically, we would like to find some material that has certain characteristics. And what we are now doing is, we would like to find some of these lamination parameters that would be realizable in a sense. So basically, without try and error, we try to create a classifier that says, we are learning this, this setup of lamination parameters could result in an existing material. And the second step would then be, okay, this is the classifier that we are learning. And the second step would then be to take this as a combinatorial optimization problem to say, okay, we would like to reach these parameters. What angles do we need to stack our layers to reach that? And this has a nice mathematical formulation that nicely fits on a quantum computer. And this is what we are doing, and also did, and we published this in a paper recently. So this is basically, in a nutshell, the idea of the first part of the project, or the first part of our lab. And the second one is more about simulation. It is about an atomistic simulation at extreme temperatures. The idea here is that we're interested in high entropy material, so material that consists of different atoms, let's say. And depending on the arrangement of these atoms, they again have different properties. And this is what we would like to investigate. For example, melting points of this material. And we have two opportunities here, basically to create, so to synthesize and examine this material, costly in time, in money, or to simulate this, also costly and timely. That's not good. So the idea is now to have a look how quantum could help here. And the idea is, on a microscopic level, on an atomic level, this is a quantum problem. And the idea of Feynman was, if you would like to simulate a quantum system, use a quantum system, aka a quantum computer. This is basically the idea. And if you would be able to do this with not too many errors, you would be, or to rephrase it, the errors aggregate. If you, at a microscopic level, have some errors, they aggregate and sum up into your macroscopic classical regime. So being very precise in this low regime helps with your output. So what we are now doing is, in this tag team, we try to use so-called density functional theory to improve the efficiency of existing high temperature methodologies to infer melting points and oxidation rates. And to reverse what I'm saying, if you are more efficient, you can use more data samples or increase the accuracy. And this again helps then with reducing the errors. So this is point one, what Philip is doing. And the second point, with classical machine learning. And the second point, what Kuhn is doing, is more staying in this very microscopic level. We try to learn and not to simulate. We try to learn the interatomic potential. And again, what I just said, it is a quantum phenomena, so it would make sense to use a quantum system to simulate this. And here, there are some existing algorithms out there called variational quantum eigensolver or quantum neural networks in general, what we just heard about, which we use to simulate, to learn this. So to combine this together, we would like to focus on some problems that aerospace has with the help of classical and quantum machine learning. And we are focusing on optimizing some laminated composite materials, and we try to simulate atomistic behavior at extreme temperatures. Thank you so much.
Thank you very much. We have some time now for question and answer. So you can ask questions to all 6 presenters, and we'll try to facilitate it with movable microphone.
Thank you.
Is there anybody who has a question?
I have one question. I recently heard the statement from someone, I won't name any names, that quantum computing will only ever be really viable for quantum simulation. So quantum computing is only going to be really useful for quantum systems and computing stuff on quantum systems. So, for example, the last presentation. What are your thoughts on that?
To Sebastian?
Yeah, and maybe some other presenters also have something to say on this.
I will give you.
This is a very radical statement. I mean, I would perhaps start there. Let's use a quantum computer for quantum simulation, but I would definitely not stop there. So I don't like this. Also, I mean, what does it mean? What do we compare? Do we want to be faster on the wall clock time? Do we want to be more accurate? Do we, So this is a very generalized opinion, and this would be my first answer to that.
Maybe I can also say something, because I also heard such a similar statement. And maybe if you go back to graphics card, at the very beginning it was also said graphics cards are good for gaming or visualization, that's it. If you now look, why is NVIDIA one of the let's say, richest company in the world? Because they sell data center graphics cards for AI. Gaming is completely uninteresting. Even HPC is completely uninteresting, it's AI. So if NVIDIA had just looked at video gaming, they would be off the market now. So I think, it's right. We don't really know which applications will function in the long run. But I'm quite sure that, let's say, just looking at quantum computers for simulating quantum systems is a little bit too narrow. So maybe, let's say, 8 out of 10 attempts we do fail, but then there are still 2 possible killer applications that are maybe not quantum systems. Right.
Okay, we had one question there, and then Peter.
Thank you.
Maybe for the last speaker, I don't know, just checking. Looking at the topic of today, it's like quantum computing and artificial intelligence, and I think I heard you saying at very last slide or something like, using quantum computing for quantum, looking into quantum issues or topics. But then you said something like using also machine learning which for me is like AI, let's say. Did I understood right, or?
Yeah, so, thank you. It goes very much also into the direction of what Eliška is doing. So in the sense of that in certain cases, a quantum neural network needs fewer data samples or fewer neurons, let's say, to solve the same task. So yeah, we are using quantum neural networks in this project, yes. And the to map it perhaps a little bit more to the energy sector, I could imagine to create some material for this turbines, for example, or to simulate batteries in this sense. So right now, yeah, we just started with material for the space, let's say, and space radiation, but the simulation can be extended, I believe.
Okay, one more question, and I think that... Okay.
I have a question for Francisco, and it also involves our moderator, because that's your field. We have in the energy system situations where we have controllers, like offshore, high voltage DC, multi-terminal things. They have to do decisions, and it's like a game, yeah? And sometimes they have to be very fast, and if they're not coordinated, they freak out and everything breaks. So that control design is increasingly challenging for our classical tradition of doing controls. And it's very complex, it's digital, so it's a nightmare. And I was intrigued by a quantum advantage in games, and distributed controls or cooperative controls is also kind of a game. They have a joint objective, but they have to be coordinated. I was wondering, how would you deploy that offshore, if they would have to share some entangled whatever you need for that, to set up a system that cooperates much better because it has this advantage. Does it make sense?
Yeah, that's a good question. It's interesting that we bring up the example of control, because so I gave the time model of load balancing as one in which there is a quantum advantage, but there's also a paper showing a similar concept that applied to a very simple problem in decentralized control and showing a quantum advantage there as well. So that's indeed a very interesting direction. The second part of your question regarding how would you deploy that offshore, and the answer is that is very, very challenging. So of course while it is true that for this particular application, the quantum system you need is simpler than a full-on quantum computer, it is still a quantum system, which means that it's very fragile, and one can certainly imagine that it will most likely be deployed at first in, say, a data center setting that's a very controlled, isolated setting rather than offshore. So how I would do it, I'm not quite sure. It's not in principle impossible, but it does look like a further into the future type thing. But I would be very interested in discussing what type of problems in the centralized control specifically you have in mind that, yeah, perfect.
Okay, so I have one more thing to announce before we go to the lunch break, the photo moment. So since the weather is very nice today, which is very uncommon at this time in the year in the Netherlands, we should go all outside. So I see the photographer is already preparing. Should go all outside, take a picture, and then have a 1.5 hour lunch break.